Hi, my name is Cedric Legenty, and I will present you our novel approach for inertial data pre-integration. The work presented in this video is published in the IEEE Robotics and Automation Letters and presented at ICRA 2020, Paris. Our paper, co-authored with Teresa Vidal-Calleja and Shudong Huang, is called Gaussian Process Pre-integration for Inertial-aided State Estimation. It extends the original concept of pre-integration into a probabilistic framework using Gaussian process regression and linear operators applied to covariance kernels. First, let me start with some context information. With the proliferation of affordable sensing devices, most of the state-of-the-art localization and mapping framework perform what we call sensor fusion to leverage the advantages of multiple sensing modalities. Thanks to their low weight and ever-decreasing price tag, inertial measurements units, IMU, became ubiquitous. This work is said to help perform state estimation for multi-sensor systems that comprise an IMU. For the sake of using an example, let us consider the scenario of optimization-based visual inertial navigation. The system's pose and velocity, denoted here by R, P, and V, are generally estimated for particular visual keyframes. The motion of the system between these keyframes is constrained by visual factors, Fc, and inertial factors, Fi. Given potentially asynchronous inertial measurements, our method aims at combining the IMU measurements collected between two keyframes. Given the sensor dynamics, the natural way to predict a future pose is to conduct classic integration of the gyroscope and accelerometer readings from known initial conditions across the integration window from T1 to T2. In the context of state estimation, the initial conditions RT1, PT1, and VT1 are also part of the state to estimate. Consequently, their values are meant to change during the estimation process, leading to numerous recomputation of the different integrals. Note that for the sake of simplicity, in this video, the IMU biases are omitted. In the paper, our derivations consider the biases thoroughly. The concept of pre-integration relies on the splitting of the rotation matrix under the integral into two parts. Thus, pseudo-inertial measurements that do not depend on the initial conditions can be computed. The original work on pre-integration considers discrete numerical integration at the IMU frequency and assumes that the measurements are constant between each IMU samples. In our paper, we present a continuous and probabilistic approach for pre-integration. It uses Gaussian process to model the inertial data and leverages the application of linear operators to the GP kernel covariance functions to analytically infer the pre-integrated measurements at any arbitrary timestamp. We evaluate our method by benchmarking against the standard pre-integration as well as against our previous work on upsampled pre-integration. The validity of the proposed technique is demonstrated in a LiDAR inertial localization and mapping framework. Before starting to present the core of our method, this slide aims at giving a rapid introduction to Gaussian process regression. GP regression is a kernel-based, non-parametric interpolation method that allows inference of the value of a signal as well as its variance for any input value. In the example here, the signal h is a function of time t. As per the standard Gaussian process formulation, let us model h with a zero-mean Gaussian process of covariance kernel k. This kernel function that takes two inputs corresponds to the covariance of the signal values at these two inputs. Given noisy observations yi of the signal, the mean and the covariance of h at any given time are computed as shown here. More details about these equations can be found in our paper or in the reference shown at the bottom of this slide. Our method produces what we call GPMs, Gaussian pre-integrated measurements. These pre-integrated measurements are results of the process shown in the block diagram on the right. One can see that the pipeline differs depending on the nature of the system rotational movement. Nonetheless, the overall steps are similar. First, the gyroscope data are modeled with GPs, and the rotational pre-integrated measurements are inferred from these continuous signals. It is done either analytically in the case of one-axis rotations or numerically for multi-axis ones. Given the rotation information at each of the accelerometer's sample timestamp, the acceleration data are projected at the timestamp of the beginning of the integration window and modeled with GPs. Finally, the position and velocity pre-integrated measurements are analytically integrated via Gaussian inference. Looking back at the rotational part of the system's dynamics, one can easily find an analytical solution to the differential equation when the system rotates around a unique axis during the integration window. It corresponds to the classic integration of the angular velocity into the axis angle representation of the orientation. Unfortunately, to date, there is no known solution to analytically integrate angular velocities for the general multi-axis case. Consequently, for multi-axis scenario, the gyroscope GP models are sampled at high frequency and numerically integrated. For the one-axis rotation case, our method leveraged the application of linear operators in the context of GP regression. First, let us rewrite the integral with the linear operator semantic. Then, by modeling the gyroscope data with 3 independent GPs, we can analytically infer the integral of the signal. If we get back to our toy example presented in the GP regression slide, we can infer directly the value of the integral as well as its variance. Further details about the application of linear operators are given in the paper. Using the steps presented in the previous slide, the rotation pre-integrated measurements are used to project the accelerometer readings back at the timestamp of the beginning of the integration window. Doing so, the integration of the acceleration data can be conducted individually for each of the 3 components. Rewriting the integrals with the linear operator notation for convenience, and modeling the projected accelerometer readings with GPs, we can directly and analytically infer the velocity and position pre-integrated measurements as we did for the one-axis rotation case. As mentioned at the beginning, the biases have been omitted in this video for the sake of simplicity. In reality, the IMU measurements are affected by additive biases that are not known accurately at the time of integration. To remedy to this issue, a mechanism of post-integration correction of the GPM based on the first-order Taylor expansion is derived in the paper. As the GPMs are designed for multi-sensor state estimation, we also propose the correction of the inter-sensor time shift in the case the sensors are not hardware synchronized. We benchmarked the proposed GPMs against the standard pre-integration and the upsampled pre-integration. The trajectories have been generated from sinusoidal functions with random frequencies and amplitudes. The windows of integration vary between 1 and 5 seconds, and the metric displayed is the average relative error corresponding to the final error divided by the distance traveled. We can see that the GPMs outperform the standard pre-integration by at least an order of magnitude. This table also shows the overall advantage of the GPMs against the UPMs, demonstrating the gain of analytical integration over a numerical one. To validate the suitability of the GPMs for inertial-aided estimation, we integrated them into IntoLAMA, our LiDAR inertial framework for localization and mapping. In the context of LiDAR inertial fusion, the GPMs are used both for combining IMU data between pose estimates and for giving each LiDAR point some information about the continuous trajectory in order to correct the inherent motion distortion present in LiDAR data. Here, you can see a resulting map. More results, whether it is for benchmarking or for the inertial-aided estimation, are given in the paper. To conclude, our work introduces a novel pre-integration method that leverages Gaussian processes and linear operators. Doing so, our method can generate pre-integrated measurements in a probabilistic manner at any arbitrary timestamp. It makes it especially suited for asynchronous sensor suits and for fusion with rolling shuttle-like sensors that require continuous trajectory information. In terms of accuracy, we showed across different simulated and real-world experiments that the GPM outperformed the standard pre-integration and the upsampled pre-integration. We released some code on our GitHub for anyone keen on experimenting with GPMs. I hope you enjoyed this video. I will answer any question you may have. Thank you for your attention.